there's a lot more like searching algorithms that exist, but these two are I would say like really common and they're pretty helpful. Okay, so the first one I'm going to talk about is linear search. So this is technically not an algorithm, but this is kind of like the basic way to to search for an element if you don't know any algorithms. Okay, so what linear search does is it searches through every element in an array and it checks each element. This is like the slowest search, but it is the easiest to implement and it always works. So um, as I said, you don't really have to understand any algorithms to do this. You just need to know the basics um, for whatever programming language you're doing. And linear search is rarely used. It's used quite a bit at the beginner level, I think. But it is much slower than other searching algorithms, um, such as the binary search. So that's the other one I'll go over. And hash tables are all faster compared to linear search. So here's an example of a linear search. We'll do a linear search practice. So for example, here we're asked to find the element 20 in a given list of numbers, and uh, the list is not sorted. So a linear search is great for these lists that aren't sorted because some of the other searches rely on it being in numerical order, like increasing order. So that's why they might not be as good as linear search sometimes. So that's why I'm gonna go over this. Okay, so we'll do this practice for I think this will probably take maybe 5 minutes. So this is the same list as last time as this picture right here. It's just kind of written into words this time. So given an array, um, it's called array bracket of n elements. Write a function to find a given element in x in this array. So just use this array. You can use any programming language you want, Python, or I have the solution for both Python and Java. So you can use either of those. So use this array, and you'll have like an input, like x, and then you want to find the index that it is located in. So I think I'll give about 5 minutes to do this. Let me know if you have questions. Yeah, I think so here's a little hint. So you want to start with the leftmost element, and then one by one compare X with each element of the array. And then if X matches with an element, then return the index that you're currently at. Okay, so it's been 5 minutes. Hopefully you have time to work on that. So I'll just show the solution. Okay, so these are just like snippets of code. It's definitely not complete. It, like for example, a Java one, you don't have the usual, um, like the public static void stuff. This is just like the stuff that is important, I guess. And also, this doesn't print out the answers. This is like a function, and it returns the value. So you'd still have to actually print what is returned. So same thing with this Java. This is just a function that returns the value. Okay, so I'll just go over like kind of how this works. So if you look at the Java one, for I in range 0 to n, so this goes from uh the first element of this array, or this goes from the number 0 to n, but it matches with the number in that, or the element in that array. So it just does a statement to test if this array or that element in this array is equal to x. If it is, it just returns I, um, which is the indexed. Remember, because that's the one we're counting up. And then if this doesn't work, then it returns -1. Okay, so that's it on linear search. Linear search is pretty basic. It's just using for loops, if statements. So all that stuff is pretty simple. So now we're gonna move on to talk about binary search. So binary search, it's still not a super difficult concept, and it is a lot faster. So I don't, we'll watch like a video later that will show you the actual code, but I'm going to talk about the concept and like how it works first. So binary search is going to um, split the values in half. So binary search only works if it's in numerical order, and it splits the intervals in half depending on where the number is. Okay, so for example, this image, it's searching for 23. So it's going to take the average of the first element and the last element. So that's going to be 91 and 2. So the average is going to be somewhere in the 40s. It's going to be like 40, 46, 47, around there. So we know that's greater than uh, the 16, which is at the half mark. So it's going to ignore the entire first half and only look at the second half because we know it's not in the first half because we did that average. Okay, then it's going to repeat that step. So it's going to look at the second half and it's going to split that in half. So it's going to take 56 and it's going to see is 23 greater than that or less than that. 23 is less than 56, so it's going to take it's going to ignore the second half of the second half. And it's only going to look at these two values and it's going to find 23 right here. Okay, so some other things about binary search, it's much faster than linear search. That's pretty obvious because you're doing a lot less searches and it divides the array into a power of 2. So what this means is the more elements there are, the faster it is compared to linear search. Because linear search, it has to search all the elements. So if there's like 1,000 elements, it has to search 1,000 times. Whereas binary search, if there's 1,000 elements, I actually have to search 10 times because 2 to the 10 is 1,024. Okay, so this is just kind of a recap of what I said. This is how binary search works. So it's going to ignore half of the elements after the first comparison, and then it's going to compare X with that middle element. If X matches with the middle element, we return the mid index. So this is I didn't talk about this step, but you can kind of get lucky in binary searches, and you can skip some steps. For example, if we were searching for 16, we split it in half, we would get it immediately in one try. So that's another way that it's better than linear search. Um, is that worst case scenario, you'll have to search that power of 2. You have to search that many times. But you can get like a better scenario where you get it almost immediately. Okay, so if X matches with the middle element, but this is rare because middle element is one element, whereas the rest of the list is much larger. So if it doesn't matches, then we say else if X is greater than middle element, then we know it's in the right half of right half subarray. So then we repeat steps 1 to 3 for that right half. And then same thing with number 5. If X is smaller, then we're going to repeat steps 1 through 3 for the left half. Okay, so last thing, we're gonna watch a short video. I think I have to stop the screen share because I didn't share the sound. So give me 1 second. Okay, so it should have sound now. Let me know if you can't hear it.
Here's a quick introduction to binary search. We're given
Real quick, we won't watch the whole thing. We'll just watch like 3 minutes.
an array that's sorted. That just means the numbers go up in one direction or the other. And given an element x, let's say, we're trying to find if it exists in this array. And also, if it exists, what's the position of x? So if x is equal to 10, say, we want to find that it exists and also that the position of x is 4. So here's binary search. Let's say x is equal to 10. So we're trying to find 10 in this array. And the way it works is we start with the middle element, or the one in the center. And if it's equal to x, then we're done. If x is smaller than this element, then we look for it in the left half of the array. If x is larger than this element, we look for x in the right half of the array. So in this case, since x is larger than 4, we're going to look for it in the right half of the array. And we're going to repeat the same procedure for this smaller subarray. We look at the element in the center, 40, and we see that x is less than this element. So now we can just look at the left half of this array to find x. And when we look at this element, we find that x is equal to 10, so we are done. So here's binary search implemented recursively. We're defining our function here, binary search, of the given array and the element we're looking for, x, and L and R. L keeps track of where the leftmost element of the current section we're looking at is. So L starts with 0, the leftmost element of the whole array. And R keeps track of where the rightmost element of the current section we are looking at is. And so R starts with 6 in this case. And if R is less than L at any point we're running this function, that means these pointers are flipped and we don't have any more elements to look at. So we didn't find X in this array. So we're just going to return -1 instead. And if that's not the case, the first thing we do here is we find the position or the index of the middle element. And we do that by L plus R minus L divided by 2. So in this case, that would be this one. So mid would be 3. If the element we're looking at, if the middle element is equal to X, then we are done. We just found X. So we're just going to return mid. If X is smaller than the middle element, then we're going to look at the left half of the array. So we're going to call binary search of the same array, the same X, and the same L. So the L doesn't change. But the new R becomes mid -1 right here. And if X is larger than the middle element, then we're going to look at the right half of the array, this part. So we're going to call the binary search the same function with the same array, the same X, and the same R. So R doesn't change in this case. But the new L becomes mid +1. Now let's look at the...
Okay, so that's all we're gonna watch for this video clip. So I think I'll give it off to Joshua and he will do, I think, a demonstration.
Yeah, cool. So we have here a visual representation of we're going to show linear search and binary search, and we're going to compare their relative speed since that's pretty important. You want to know how fast binary search actually is. So this is going to be, I'm going to have a visual demonstration, and then we're going to have a giant, or we're going to try to input a giant set of array to see how fast it would actually be if we have a huge amount of numbers to work with. So with this smaller set, we can visualize pretty well. So let's say maybe you want to look for 328. If we do linear search, you can see it'll match through every single number one at a time, as Lucas has mentioned, and also, yeah. So it goes through one at a time, and it's obviously very slow. It's going to take a while to get there. And if we use binary search instead, you'll see it kind of cuts it in half, and then it cuts it in half again, and then it just finds number pretty fast. It was a lot faster than this. So you can see this is a pretty good visual representation of binary search versus linear search. Linear search will repeatedly cut it in half and until it finds a value. And now we're gonna move on to the more interesting one. This is the we're gonna use linear search and binary search to find one number in basically a giant array. So this is going to be the set of numbers we have, and I can't actually open it in the code editor because it's a bit too big to open it. So we're gonna use Notepad instead. So you can see it's 30 megabytes, so that's pretty big. And if we open it up, you can see that this is going to be the set of numbers to look for. So obviously, you can already tell that linear search probably won't be an ideal option here, since it's going to take a very long time to look through all these numbers and find one number in this giant pile of mess. And binary search can actually cut that time down a lot. So what we're going to see here is we're going to compare the speed now. So we have linear search here. Get this out of the way. Okay, so linear search, when I hit, I actually made the code a tiny bit slower by adding print statements so we can just see what it's doing. So it'll be a bit slower than it actually is, but their relative speed will remain about the same. So let's give it a try. This is linear search. And as you can see, linear search is checking through every numbers. So it's going to just count up basically until it hits a number. And here we have some of the more important information. They found the index. So this is what position the number we're looking for. In this case, I put down a number beforehand, which is about 7 million. And it found it at the index of 3 million. The number of iteration it took is obviously one more than the index since the index count up from 0 all the way up to the number. So since it goes through each of them one at a time, the number of iterations it'll take, the number of comparisons it'll make is basically one more than what the index is. And the time it took, this is I think it's in nanoseconds. I use time.nano here, as you can see here, to compare the amount of time it took from the beginning to the end, and it's about 5 billion. I guess nanoseconds is what it is measuring. So obviously that's not very efficient, especially if you have, let's say, even bigger ones, maybe instead of 30 megabytes, it's like uh, gigabytes, terabytes, and so forth. So this isn't efficient. But now if we switch to binary search, um, and we run it now, you can see that took barely any time at all. It only checked 20 times. There was only 20 iterations, which means only compared 20 numbers total compared to the previous 3 million numbers. So that is a huge time save. And you can see the time here is in the millions of a nanosecond instead of the billions. So that is like thousands of times faster. So this is, you can see, proof that binary search is way faster than linear search. Yeah. So you got 20 iterations compared to 3 million iterations, and you got 6 million compared to a few billion. Hmm.
Um, should I go over the jump search and interpolation search, Lucas?
Um, I think so. Josh, that's it, right? Yeah, I think you can go over that then.
Okay, let me pull out my notepad. So jump search is another type of search. It's pretty interesting. So basically, linear search is O of n time, right? So like it takes a quite amount of time if n is very big. And in binary search is O of log n time. So linear search is big O of n, and in binary search is big O of log n. And then there's another one, it's called jump search. And this one is big O of square root of n. So it fits right in between. And jump search, for jump search, right, there's a couple things that need to happen first. The array needs to be sorted. So it's exactly like binary search. It needs to be sorted like binary search. And then so you might be thinking like, why do we use jump search over binary search? And the reason is when the scenario is that like binary search takes if binary search takes a long time, it might have to jump backwards a lot, right? Because you're cutting by half each time, and if you over jump by half each time, you might have to go backwards a lot. And then so in scenarios where it is like quote unquote costly to go backwards, that's when you want to use jump search, because jump search only needs to go backwards once, and binary search needs to go backwards however many times because it's jumping by half each time. The way jump search works is it jumps from index 0 to index 0 plus square root of n plus index square root of n plus square root of n. So it just like keeps jumping in multiples of like whatever number. And normally it's been calculated that the most efficient number to jump between each block is square root of n. So if you have an array, and let's say you have an array of 0, 1, 1, 2, 3, 5, 8, whatever, all of this. So we can count how many numbers are in here, right? So this is 0, 1, 2, 3. All right, this might take a while. So let's just count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 16 numbers, right? 0 to 15, 16 numbers. And then so your the size of your jumps would be, which is m, would be equal to 4, which is square root of 16. So your first check is you would check right here. So this is where you would check first, and then you jump 4 numbers and you check over there and you keep going. So let's say you wanted to find like the number 55, right, which is right here. What you do is you check 0, and 55 is greater than 0, so you jump to the next block, right? So plus 4 indexes, so it would be this one, right? 1, 2, 3, 4, yeah. And then you check this one, and then 3 is also less than 55, so you jump 4 more, right? So you check 21, and then 55 is greater than 21, so you jump another 4, which would bring you to 144, right? And when you get to 144, 55 is less than 144. So once you get here, you can quote unquote jump backwards. So you can simply jump to 21 and start linear searching between 21 and 144. Or you could just start at 144 and linear search backwards, right? Check 89, it's not equal, and then check 55, and it is equal. And then so it takes a bit longer, right? It's square root of n, but its benefits is that it only has to jump backwards only one time, which is why it's used at all. And then you might be thinking like, what are examples of its use? I couldn't find any really good examples, and I don't know any really good examples except if you're like on YouTube. I'm sure you guys know what YouTube is and how it works. So if you guys know on YouTube, when you click on numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, it brings you to that like percentage of that video. So like if I'm watching a YouTube video and I click 5, it'll bring me to the halfway point. And similarly, if I click 0, it'll bring me to the start. And if I click 1, it will bring me to like the 1/10 part in, if that makes sense. So let's say I'm watching a video and I'm trying to search for this one part, or like this one like scene or something, right? Or one frame. And then I don't know where to start, right? So you have options. If you were to do linear search, you just watch the whole video until you reach the frame, which isn't really smart. And if you do binary search, you would go start in the middle, then you jump to the next half, whatever. But no one really does that because you're watching a video and you don't want to have to like, binary search your way through. What most people do is jump search, right? Although they don't know it's called jump search. You'd probably, right, you either hit the right arrow and then you keep speeding by 5 seconds, or you hit L, right, which speeds you by 10 seconds, or you use your numbers, right, 0, 1, 2, 3, 4, and you keep going that way, and then you keep on going, jumping by blocks of 5 seconds, 10 seconds, or even 1/10 of the video until you reach a point where you are past that frame, and then you start going backwards. And so that's kind of like an example of jump search that you've probably used before. And then there's another search. It's called interpolation search. Um, this one's also kind of interesting, though it has a bit more requirements. So the array also needs to be sorted, like bin search, and jump search, right? It also has to be sorted, and to be used properly, the array needs to be distributed. So what that means is like 0, 1, 2, 3, 6, 7, 8, 11, 12, 25. That's not uniformly distributed, right? The gap between each number is not uniform. Well, a uniform distribution would be like 0, 1, 2, 3, 4, 5, 6, right? Or 0, 2, 4, 6, 8. The gap is uniform. And so it's very similar to binary search, except it doesn't just jump by half each time. So it starts at the midpoint and then it checks if it's greater than or less. If it's greater than, instead of just simply jumping to the midpoint of the right side, it instead has a formula to calculate which position to jump to because the values are uniform. So I'll show the formula later, but one way to think about it is it's like if you're looking through a phone book, right? And then you are looking for a person whose last name starts with like Y, right? And then if you do linear search, you just start from the front and go all the way to Y. That takes a long time, unnecessary. If you do binary search, you're gonna start in the middle, start at like the middle. I don't know what the middle one is, but middle, and then you jump towards the right, and then you ultimately end up at Y. But it's also gonna take a lot of time, especially because you know, like the last name has to be in the Y category. So there's no point even to consider every single other category. You should only search the Y category. So it's kind of the same concept as that. Basically, it knows the uniform distribution. So it therefore knows that, like, if I'm looking for this number and it's greater than this number, you can take like the difference between those two numbers and kind of figure out a better value to search for instead of just jumping to the midpoint. The formula to use to find that next midpoint or area or value or whatever is this. It's basically low, which stands for the lowest index, the starting index. So like this person, 0. And then X is wherever you like are looking for. So if I'm searching for 55, my X will be 55. Array of low, we know what that is. High is the last index, or the 7 in this case right here. Subtract low, we talked about that. Array of high, we also know what that is, and array of low. And that's basically how it works. If I'm going to be honest, I don't really know how any of this math stuff works because I've never used this search at all before. But that's basically how it works. This is like derived from y equals mx plus b, or m to the power of x plus c. Though I also don't know how that works. You guys can research more about that if you're interested in it. But the formula, or like the function, basically, it works very similar to binary search, except each time, instead of just dividing by half and choosing your next position, you simply like replace the position with this, and you'd find a better position using this. So if done right, if done correctly with the correct parameters, interpolation search, I believe, is O of log n. So it's like super, super fast. But yeah, it's very rarely used because your array needs to be uniformly distributed. I think that's all we have today. If you guys have any questions, guys can let us know. Otherwise, I think we're just gonna end the meeting. All right, I'm going to end the meeting.